Let's look at another example. Consider a hollow collet chuck that's typically seen on lathes. The chuck is experiencing purely axial loading with F equal to 1,000 kilonewtons. OD1 is equal to 160 millimeters, OD2 is equal to 120 millimeters, the inner diameter is equal to 80 millimeters. L1 and L3 are both equal to 25 millimeters, and L2 equals 100 millimeters. We want to determine the average normal stress in each component of the collet chuck. We'll start with a free body diagram of the collet chuck in 2 dimensions. With each component, we'll make an imaginary cut and determine the internal reactionary forces by employing a force balance, i.e. our equilibrium equations. Starting with the left collar, our equilibrium equation for the x direction tells us that R is equal to negative F. Recalling the formula for average normal stress is force per area, the average normal stress with this component's geometry will be equal to negative 4F per the quantity pi times OD1 squared times ID squared, since the area of a circle is pi d squared per 4, and we're subtracting the area of the hollow inner diameter. The stress in component 1 is then equal to negative 4 times 1,000 kilonewtons divided by the quantity pi times 0.16 meters squared minus 0.08 meters squared, which gives us an average normal stress equal to negative 66.3 megapascal, and we note that this component is in compression. Moving on to the second component, the sum of forces in the x direction is equal to 0. Therefore, R2 must be equal to negative F. We'll use the same formula for average normal stress as we did with the previous component. This gives us negative 4 times 1,000 kilonewtons divided by the quantity pi times 0.12 meters squared minus 0.08 meters squared, which gives us an average normal stress of 159 megapascals. We can note that this component is also in compression. Considering the last collar, the sum of forces in the x direction equals 0, which means that R3 equals negative F. The average normal stress in the member is then equal to negative 4 times 1,000 kilonewtons divided by the quantity pi times 0.16 meters squared minus 0.08 meters squared, which results in an average normal stress of negative 66.3 megapascal, and we note that this component is also in compression. Note that for this problem, the average normal stress in components 1 and 3 is the same because they're experiencing the same force and have the same cross-sectional area. The average normal stress in component 2, however, is higher. Although it experiences the same force as components 1 and 3, it has a smaller cross-sectional area, and thus the stress generated is higher. Let's consider a slightly different scenario, where different amounts of force are being applied to sections of a member. Here, 3 people are tugging on a rope attached to a stationary box, as shown below. The person farthest from the box is applying a load of 1 kilonewton, the person in the middle is applying 1.3 kilonewtons, and the person closest to the box is applying 1.4 kilonewtons, and we want to find the average normal stress within each section of the rope, given the rope has a cross-sectional area of 20 centimeters squared. We'll start by drawing a global free body diagram, which shows that since the box is stationary, it's exerting a reactionary force R on the rope to oppose F1, F2, and F3. We can solve for R by applying the summation of forces in the x direction. Since the sum of the forces in the x direction is equal to 0, negative R plus F3 plus F2 plus F1 must also equal 0. Rearranging this equation and plugging in our known values, we get that R is equal to 1.4 kilonewtons plus 1.3 kilonewtons plus 1 kilonewton, or 3.7 kilonewtons. We'll break this problem down by doing each section of the rope individually. Drawing a free body diagram of section 3, we can see that R and R3 are acting within the rope. Note that we're not using F3 in this equation because we're concerned with the forces internal to the rope just before the point of application of F3. To find the value of the internal force R3, we can use the sum of forces in the x direction. The forces in the x direction sum to 0, so minus R plus R3 must also equal 0. Rearranging the equation, we see that R3 is equal to R, which is equal to 3.7 kilonewtons. We can now input this value into the average normal stress equation, R per A, which is equal to 3.7 kilonewtons per the cross-sectional area of the rope 20 centimeters squared to get 3,700 newtons per 0.002 meters squared. And this value gives us an average normal stress of 1.85 e to the 6th Pascal, or 1.85 megapascal. We'll repeat the process for section 2 of the rope. Looking at the free body diagram, we see that R, F3, and R2 are contributing to the force in this section of the rope. Since the sum of forces in the x direction is equal to 0, minus R plus F3 plus R2 must also equal 0. Rearranging and plugging in known values gives R2 equal to 2.3 kilonewtons. Plugging this into the average normal stress equation, we get 2.3 kilonewtons divided by 20 centimeters squared, which is equal to 2,300 newtons per 0.002 meters squared, and we get an average normal stress of 1.15 e to the 6th pascals, or 1.15 megapascals. Lastly, we'll apply the sum of forces in the x direction for section 1 of the rope and see that minus R plus F3 plus F2 plus R1 is equal to 0. Solving this gives R1 equal to 1 kilonewton. The average normal stress in this section of the rope is then equal to 1 kilonewton per 20 centimeters squared, and dividing this gives an average normal stress value of 0.5 e to the 6th Pascal, or 0.5 megapascal.